Okay, this is our last problem in lesson 2.8 here, and it's very, very involved. Okay, it starts off here that in a certain city, it's giving me the number of daylight hours on the summer solstice and then the number of sunlight hours on the winter solstice. So obviously in the summer, the days are definitely longer. You have more sunshine. The winter, the days are definitely shorter here. Now, we're going to answer these questions here. I'm going to write the questions down. I didn't paste those in there. It said assume that the summer solstice occurs on the 172nd day of the year, and that there are 365 days until the next summer solstice. That's 365 days in a year there. Now, the best way to look at this is to try to figure out a graph here. And so the first question is going to ask you here is it's going to ask you to find a sine function in this form. So let me write the form out here. So y equals a times the sine of omega x minus phi and then plus b. Okay, so let's start off, and what I actually do to help me figure this out is I actually draw the graph first. So I'm going to draw a graph, and you'll have to kind of follow real close here along with this on how I get these values. And so along the y-axis, what I'm going to put is the amount of sunlight or the hours of sunlight that we're getting in one particular day. And so notice that ranged from 8.568 to 15.978. So the lowest amount of sunlight that we've had, that would be on the winter solstice, that would be the shortest day of the year, would be 8.568. Okay, so that's like for a certain city. I'm sure cities in the north probably might be less than that. Cities down south, we'd have a little bit more than that. Now, the most amount of hours that we'd have in a day would occur on the summer solstice, which is the first day of summer. And so we're given that's 15.978. Okay, so now what we want to think about here is if it's a sine curve, then it's a curve that's just going to bounce back and forth between those two values. All right, so kind of get that picture in your head there a minute. Now, what we need there first is the center line, because we have to have sort of like the zero, kind of like the x-axis is on most of our graphs. So let's get the idea here that what we want to find is this value that's dead in the middle there. It's actually probably a little bit lower than that. So about right there. And so let's see how we can calculate what that is. So first, let's find the distance between the high point and the low point. So to find that distance, all I've got to do is basically subtract these two. So we'll say 15.978 minus 5 or 8.568. So here that we're getting that distance is about 7.41. All right, so understand the distance between from here to here, that's a difference of 7 hours. And so the center line is basically just going to be half of that. So now I'm going to take in my calculator and punch in there 7.41 divided by 2 to find that midpoint. So 7.41 divided by 2. Now, that's going to give me here about 3.705. So now what we've got here is this distance halfway from there to there would be 3.705. So see if you can kind of figure out what that actually is representing there. That would be the amplitude. Okay, so we actually have just figured out the amplitude by drawing the graph. So let's actually write that down here over to the side. The amplitude is going to be 3.705. Now, the center line would be 3.705, but it would be 3.705 units away from either this top value or this bottom value. So let's add that there. So I'm going to do the 8 one. 8.568 plus 3.705. And so this center line now is going to be 12.273. Write that a little bit neater there. So again, this would be 12.273 is going to be our center line. Now, that actually tells me something else in here. So the graph has been shifted up from the x-axis to that point. So think, well, what does that value represent? Well, that's our vertical shift. So our B, or our vertical shift, is going to be 12.273. Now, let's find the other values that we need. So that would be this and this. So the easier one here is definitely to find the omega variable. And so what we can do is find it from the period. So we haven't really mentioned anything about the period here. Let's think about it from what the problem says. So notice that there's what, 365 days in a year? That's our period. That's how long it takes for the summer solstice to cycle through there. Okay, so we've kind of established here, since they were talking about a year, that the period would be 365 days. Okay, now think of what we would do here to kind of increment it. Well, normally we take our period, which would be the 365, and divide it by 4 to get the count by. Okay, so let's go ahead and get this variable here, and then we'll kind of go to the count by. So let's think about, how do we calculate the period? Right, the standard period for sine is 2 pi. So we would say 2 pi divided by 365. So there's our period. Now, we're going to, they're going to ask you here, they're going to say leave it in terms of pi. So I'm going to leave it like that, and I'm not going to divide it. Now, let's think about what each increment here is going to be. So 365, what we normally take the period and divide it by 4. Okay, so we would take 365 there and divide it by 4. Or let me think about this. I'm sorry, I messed this up. Let's back up. So our period, I'm sorry, is 365. Okay, I kind of got a little backwards there. What we're trying to find is that variable omega. So recall this here. The period is equal to 2 pi over omega. Now, we've just sort of figured out here that the period would be 365 days. So we'd say 365 equals 2 pi over omega. Now, let's solve for omega there. So we would cross multiply. Move this out of the way. So we get 365 times omega equals 2 pi. And now we're going to divide both sides by 365. And so we're going to leave this in terms of pi. So our omega there is going to be 2 pi over 365. And so just a minute, we will substitute that value right there. Now, before I think about the phase shift here, which is basically going to come from this value right there, I'm going to go ahead and sketch in the curve. And then I'm going to figure out what can I do about that? How can I shift it over? Now, to sort of do all this, we'll need a little bit of room here. So I'm going to take away all these calculations. We'll leave those over there on the side because I still need those to write my equation with here. Now, let's think about what the sine function looks like. Okay, we've got the center line, and then I'm going to draw sort of a line for the top line there. So the maximum and then the minimum. So what happens with this is we can draw us in a sine curve. All right, so remember, sine starts at 0, or at this case on the center line, and goes up. Now we didn't put our count bys in there. I kind of skipped that. So let's go back over that the period was, this is what I was getting to earlier before I'd messed up, is 365 days. But we're going to divide that by 4. And if you think that, that kind of makes sense because you're dividing it up into the 4 seasons. So I'm going to divide in my calculator. 365 divided by 4 is 91.25. So I'm going to have 4 increments here. So 1, 2, 3, 4, counting by 91.25. So 91.25, and then another 91.25 is 182.5, and then another 91.25 is 273.75, and then of course another 91.25 would give me my end there, 365 days. And so we sort of divided up here the seasons of the year. Now let's sketch in a cosine, or excuse me, a sine curve. So sine starts at the center line and then goes up here. So it would go up at the 91.5, back down to the center line at 182.5, down to the minimum at 273.5, and then complete the cycle here, back up to the center line at 365. So now let me draw in the curve. Okay. Now, notice we haven't said anything about phase shift and about this idea here. So supposedly here on the 172nd day, that's the summer solstice. So in the summer solstice, you're going to have the maximum number of light. So my graph doesn't make sense here. If this was the first day of the year there, then, you know, really the first day of the year, the January, it's kind of colder. You don't have a lot of light. So what we want to do is we want to take this maximum point, which is at 91.25, and we want to shift it over to 172. That's our idea here. So notice 172 would be a right along in here somewhere. So what I'm going to do with this is I'm going to have a phase shift. So I have to shift the curve so that this maximum point lines up with this 172nd day. And so basically what we're going to do is we're going to take the curve and sort of move it over like that. And so there my high point would line up with 172. Okay, so now what I just did was figured out the phase shift. So notice if I shift it over from 91.25 over to 172, let's think, how could we figure out, well, how far over did we move? Well, that's not really hard math. All you have to do is just subtract that. So I'm going to subtract that on my calculator. So 172 minus 91.25 is 80.75. So now I've just figured out that phase shift. So again, what I did there was say 172 minus 91.25. I just punched it in on my calculator. And so this gave me 80.75. So now let's sort of add it to the list of values that I'm kind of compiling over here on the right side. So we've got now that the phase shift is equal to 80.75. Now, what I need here for my equation is that variable there, okay, the variable phi. So let's take the phase shift and let's see if we can calculate that now. So here again, let me get rid of all this calculations right here. And so recall this, the phase shift is equal to phi over omega. Okay, well we know that the phase shift is 80.75. All right, we're trying to figure out what phi is. Also trying to draw it right. Over, now we just figured out what omega was here. So remember there, omega was 2 pi over 365. Okay, and so now what we're going to do is just cross multiply. So 1 times phi is phi. And now when I'm calculating this, 80.75 times 2 pi over 365, it's not going to let you use a decimal. It's going to make you do it in terms of pi. So what I'm going to do in my calculator is just punch in 80.75 times 2 pi, and it'll be whatever that is over 365. So 80.25 times 2 pi, or I'm sorry, just times 2 because I have to leave the pi in there. I'm sorry. So let me back up again. 80.75 times 2 is 161.5. So this would give me 161.5 times pi over 365. Now I put that in as my answer, and it said it was correct, but it wasn't in the right form. So the deal is you can't have decimals in that. So I'm going to flip over here and show you how we can take care of this on the calculator to kind of how that they want that. So give me a second. Go back. Okay, here we go. So you can see the calculator now, hopefully. And so again, what I'm trying to do is take that value there, that 165 pi, and switch it here so that it would be a fraction. Okay, so kind of watch real carefully here. I'm having trouble seeing the bottom part of this. Let me pause it and fix it. Okay, I think I finally got this set up here where we can see this. So the problem here is that's in a decimal value, and so they want everything to be as integers or fractions. So what I'm basically going to do is just turn 61.5 over 365 to a fraction with no decimals using my calculator. So I'll divide here 161.5 divided by 365, and so that gives me a decimal value there. But then I'm going to take that decimal value and just change it to a fraction. So to change it to a fraction, I want to use that PRB button that switches a decimal to a fraction. So hit second and then PRB and then hit equals. And then now we've got a decent fraction there that doesn't have a decimal. And so we've got 323 over 730. And notice I didn't say anything about pi. I couldn't punch the pi in because that would mess my fraction up. And so I'll just bring down the pi there. Okay, so now finally, after this 3 years of long hard work here to get all these values, we're going to actually take them and put them to the equation, and we're finally going to have our equation here. So notice here, that's our equation. We found all those values, the amplitude, omega, phi, and then the vertical shift. So we'll get y equals, okay, recall A, the amplitude we found was 3.705. Now, times the sine, I'm going to have to kind of write it below here, of omega times x. So look back what omega was here. It was 2 pi over 65, so over 365, 2 pi over 365 times x, all right, minus rho, or excuse me, minus phi, which was the hardest one to find there, 323 over pi over 730. And then plus b, I know this is kind of like stringing along there, but it's a lot of work. It kind of run out of room. Plus their vertical shift, or the b as they're calling it here, the 12.273. So finally got all this for my equation now. Okay, now they're going to ask you a question here, and so let me copy this, and we'll go to another slide here. Okay, so there's our equation. Let me actually fix it up a little bit here for us. Well, never mind. We'll just leave it like that. Now, the question will be something to this effect. They're going to ask you predict the number of hours of sunlight on a particular day. Okay, so this question on this one says use the function to predict how many hours of sunlight will be on, I think it says, yeah, the 91st day. Okay, so it's really not that hard. Getting the equation was definitely hard. So once you get the equation, this question is not hard to answer because x here is the number of days. So all we have to do is take 91 and then substitute it there for x. Now that's a lot of calculations to do there. So what I'm going to do is kind of rewrite this and put these as decimals, but I'm going to store them on my calculator. Okay, and this would make it a lot easier here for you to sort of do. So I got 3.705 times the sine. Now, hang on. Okay, and so now what I'm going to do is do 2 pi divided by 365, and it'll be times 91. I'm going to do that all on my calculator here. So I'm going to just tell you what I'm pressing in here. I'm doing 2 pi divided by 365. Okay, so that's about 0.0172 something or another. Now, times x, and what we're going to put for x there is we're talking about the 91st day. So I'm going to say times 91. Okay, and so I'm getting about 1.566 here. And what I'm going to do is store that, and I'm going to store it in the value of a. So remember how we can store values into the calculator here? So I'm sorry, I messed up. I didn't say times 91. Let me back up and do that again. This will be 2 pi divided by 365 and then times 91. Okay, that was right. So 1.566. And so I'm now going to store that in the value of A. All right, minus. Now I'm going to calculate this in my calculator and store that. So it'll be 323 pi divided by 730. And so I'm getting there. That's about 1.39. And there again, I'm going to store that. I'm going to store that one in B on my calculator here. And then finally, plus 12.273. Now let's finally throw all this in. So I'll punch in 3.705 times the sine of, now I'm going to recall A, minus, and then recall B, and then close my parenthesis, and then add 12.273. Okay, so this gives me about 12.92. And so that's how many hours of daylight we would have on the 91st day. Okay, the last thing that you'll have to do is actually the easiest of all. You have to pick which one is the correct graph. Now, instead of looking at our graph, which was a little bit off because we were supposed to shift it here, look at the idea that the summer solstice was on, again, the 172nd day. That means that's the day that you would have the most amount of sunlight. So at 172 should be the maximum, and that's what's going to give away the graph. So notice on 172, which would be somewhere right along in here, that's the maximum there, so that kind of makes sense. Kind of makes sense on this graph too, but we'll find something wrong with that one. And certainly the other two at 172, that's not a maximum there. And the maximum here on this graph, that doesn't occur at 172. Now, if you'll go back and remember the amplitude is what's going to help me on the other one. The amplitude goes from about 8.5 to 16. So 8.5 to 16 here. Okay, it's kind of hard to tell. I guess you'd have to blow it up to see. That's just a little bit too low right there. And so 8.5 is more halfway in between. There's where it starts very, very subtle, but that gives you that one there.